Alright, so in this video we're going to talk about parametric or parametrized curves in the plane. So what that's about, alright, is really just a new alternate way to describe curves geometrically. You've probably thought about curves in terms of graphs, maybe even as equations. Well, now we think of them in terms of a parameterization. So a parameterization of a curve is a pair, alright, it's a pair of equations, if you will. But I actually prefer to think of it as a function, a pair of functions that go together. So to me, the most natural way to think about a parameterization actually as a vector valued function, which is what this notation indicates. It takes in a real parameter t and it spits out a point in R2, which you could think of as a vector. So in other words, a parameterization is a pair of functions, and that defines a parametrized curve, or sometimes we call it a path. Now the image of that path, the set of all points which it reaches, R of I, this is some set image notation. You'll learn more about that in Math 200 if you take it. But anyway, it's the set of points that if you plug in the time in the domain of the parameterization, then you spit this out. So here t could be time, it could be something else. Oftentimes I think of t as being time, but really it's just the parameter. Now here's perhaps a good example. Here we have x equals to cosine t, y equals to sine t, and 0 less than t less than pi. I say that this parameterizes a circle with radius 1, but to be precise, it really only parameterizes the upper half circle like this. We draw these little arrows to indicate the direction of the curve. So that's something new. You know, if you just look down here at the Cartesian form of the circle, x squared plus y squared equals to 1, you can't really tell that it's got a clockwise or counterclockwise orientation. But this parameterization of the circle, the half circle really, does have a counterclockwise parameterization. As time increases, we go from 1, 0 to over here to minus 1, 0, right? So that's something new. The parameterization gives us a sense of direction. Parametrized curve is an oriented curve. It knows where it's coming, where it's going to, where it's coming from. It's got an orientation. Another concept that's useful for this discussion is the concept of a level curve. And so a level curve is this. A level curve, or implicitly defined curve C, is given by an equation. So we've got some equation f of xy equals to L. And to connect these two concepts, if we have x equals to f1 of t and y equals to f2 of t, such that when we plug those parameterizations for x and y into here, into the equation, we get back, we solve the equation for all time in the parameterization. Then this pair of functions, parameterizes the level curve. Notice, by the way, that the level curve is the inverse image of the level L. It's the set of all points x, y in the plane, such that when you plug them into the level function f is the level function. Alright, we'll talk more about that in Calculus 3, but I think it's useful to say a few words here, so I am. The level function, it's an inverse image. It's the set of points in the plane such that when you plug in those points, you get L. In contrast, the parameterization is a forward image. Alright, so collecting our thoughts here a bit. On the other hand, of course, we have graph. Let's not forget about that. A graph is the dominant viewpoint. Up to this point in your mathematical career, you think about y equals f of x, and if you want to get picky, the graph is the set of pairs x, y, such that y is equal to f of x, and x is in the domain. That's a subset of R2. So if you think about it, we could take a graph and we can either view it implicitly or explicitly. Explicit viewpoint is the parametric viewpoint. You think about x being equal to t, y is equal to f of t, t is in the domain of f. In other words, we can think of a graph as a parameterized curve where x is used as the parameter. On the other hand, we could look at a graph as a solution to an equation namely that f of x comma y equals to x x minus f of x. Oops, that's wrong. I meant to put, oh no. Yeah, let me fix that. That's why I'm doing this in part. That's supposed to be a y. There we go, fixed. Y minus f of x gives, when that's 0, that means that y is equal to f of x, right? And that's the graph. So since a graph is written in terms of Cartesian variables, it's easy to come up with a Cartesian equation which recovers the graph. All right. So generally a graph is a parameterization where we use one of the Cartesian coordinates as a parameter. So I think of a graph as kind of being a middle ground between the parametric viewpoint and the level curve viewpoint. All right. And all three of these viewpoints are important. Now we're going to focus mostly on parameterization for the rest of this video, but we'll talk a little bit more about, the Cartesian viewpoint. So here it is. X squared minus y squared equals to 1 is a hyperbola. I think about this, if I think about y equals to 0, that gives me x squared equals to 1, which tells me x is equal to plus or minus 1. So that gives me these vertices here and here, right? Now, so here's the right branch, which is parametrized by that. All right. And the reason I know it parameterizes the right branch is because cosh is larger than or equal to 1. So it's going to be the right branch. The left branch, on the other hand, over here, right, that has x less than or equal to minus 1, right? So that right there is minus 1. And on the other side we have 1, yeah, x equals to 1. So, sorry, I'll stop eventually. Anyway, my point here is that this is a parameterization down here of the left branch because, and by the way, the reason both of these are parameterizations of the hyperbola is you can check that x squared minus y squared, which is cosh squared minus sinh squared, or minus cosh squared, which is just cosh squared, minus sinh squared is equal to 1. If you plug these equations into the Cartesian equation, it works. And over here, y squared minus x squared is also a hyperbola, but this time if we put x equal to 0, we get y is plus or minus 1, right? Which is going to give me, like, for example, the upper branch of this hyperbola is up here. We can parameterize it by y equals to cosh t, x equals to sinh t. Now sinh takes on all values as t ranges over the reals, which is what I want for that. I want x to be unbounded, positive and negative, but I want y to be larger than or equal to 1, which is what I have with this formula. That makes sense to me. And also if we plug it in, we get cosh squared minus sinh squared, which is 1. Now on the flip side, example 3, as a graph, we could solve this for y is equal to the square root of, y is equal to the square root of 1 plus x squared, right? And that would be a graph which reproduces the upper branch of the hyperbola. All right, oops. So moving on here. If you don't know about hyperbolas and circles, well, you probably should do some reading. I think there's a good section in your text. Here's a circle of radius 2, and my question is, I'm looking at the quarter circle between y equals x and y equals minus x, all right? And with x positive. So that, if you think about it for a little bit, that focuses you in on this piece right here, right? See, because where x is positive and y equals to x, this x is like up here, right? And the y equals minus x is down here, and I'm on the right side of the y-axis because we're assuming that x is not negative, right? So you see we're just that little piece of the circle, and we can parameterize that with x equals to 2 cosine t, y equals to 2 sine t, and geometrically you can think of t as being the standard angle in something called polar coordinates. So no spoiler alert. Well, we'll get to it soon, but you should already have actually seen polar coordinates before this course, I would hope. But anyway, here you go. X equals 2 cosine t, y equals 2 sine t, and minus pi over 4 less than t less than pi over 4 will do nicely to get me that that curve right there. And it's an oriented curve with this parameterization, and it goes like that, right, in the direction of increasing standard angle, counterclockwise. Now here's the general bag of tricks. The line segment formula. To parameterize the line segment from P to Q, we can use this vector formalization. R of t is P plus T times Q minus P. Here, just work it out. I mean, plug in 0, you get P. Plug in 1, you get P plus Q minus P, which is just Q again. So you can see that it works. By the way, Q minus P is the direction, it's the directed line segment from P to Q. It's right in terms of high school geometry. It also gives us the direction vector of the path from T to R of t. So here's a picture of that path, and so it's kind of an abstract picture, but there it is. Now let me give you some numbers, and don't want this to be a pointless exercise. Here's some points. All right, so from 2, 3 to 8, 6, I use the general trick I just shared with you, and that gives me 2, 3 plus t times 6, 3, which when I this becomes 6t comma 3t, and so I add those, I get 6 plus 2 plus 6t and 3 plus 3t, which we could typically write as x equals to 2 plus 6t and y equals to 3 plus 3t for 0 less than t less than 1. I have much more written in my lecture notes, and your text also offers further insight here. By the way, I'm also taking the viewpoint, a somewhat, what's the word? Relaxed viewpoint about vectors right now. I haven't really formally introduced them. I'm just working with them with the assumption that you'll pick it up as I do it. Now, that's not ideal. I would give a more formal and organized treatment of vectors in Calculus 3, but here, for the moment, they're mostly just a notational device for us, okay? Here's another one. Example 8, find the Cartesian form of the curve given by x equals 3 plus cos t and y equals minus 2 plus sinh t. So the key identity I think about here is that cos squared minus sinh squared is 1. So I solve this for cos, I solve that for sinh, and then I plug it in, and that gives me x minus 3 squared plus y minus 2 squared minus y plus 2 squared equals to 1. And that's a hyperbola centered at 3 comma minus 2. And but actually, when you look at the original equations, because x minus 3 is cos t, we get x is greater than or equal to 4, which goes to show you that we're getting the right branch of this this hyperbola there. And I guess I can add a. Let me add it in here. Let's see, so it's centered. You foolishly attempt a picture here. So it's centered at 3 and minus 2. Let me make this smaller. Let's see. So over x3 down 2, so something like that is its center. I can tell it's got asymptotes with slope 1 just from eyeballing it. So it's something like that. That's the asymptotes to the hyperbola, and I was just arguing that the given parameterization, it's got the right branch of this hyperbola, something like that, is what is actually parametrized, what is given to us. All right. So that center point there, as I was just advertising, this center of the hyperbola is at 3 comma minus 2. I can see that from the boxed equation. All right. Next up, find the Cartesian form of the path given by x equals to e to the 2t and y equals e to the 3t minus 7. So this time I look at e to the t as a common weakness. So on the one hand, I've got x is e to the t squared. On the other hand, I've got y is equal to e to the t. Well, e to the t cubed is y plus 7. So if I cube the first one and I square the second one, I get a common e to the et to the 6th power. And so that gives me y plus 7 squared equals to x cubed. And I can even find a graph of this by taking the square root and noticing that I can choose the plus because y is greater than minus 7 in the given problem. And so there you go. That's a graph which covers the parameterization here. So I think that brings us, what's up next here is the calculus of parametric curves, and then I have many more examples. I have a few tests I'll work through here eventually. Thanks.